Greetings, Algebra 2. If you're watching this sometime other than March of 2020 during the coronavirus, please excuse the next minute or two of foolishness because you just won't get what's really going on here, I don't think. But where we are these days in the world of TMR the Math Wizard's development, at my last count I was up to about 30 subscribers-ish, so as near as I can tell, only 970 more until I start to get paid, so we all have that to look forward to, I suppose. I also in recent events got my account verified, which means I can now post videos up to 12 hours in length, if you could imagine such a thing, but I promise I will not subject you to any 12-hour videos for your sake, and also I can't even imagine how long it would take to upload a 12-hour video on the internet. It's almost incomprehensible. We are in 9.2 now is where we are, so if you're watching this video sometime here forward, this will make more sense and be more applicable to your life, I suppose. But 9.2 is about a thing called transformations. You should have a notes paper in your packet that explains that transformations are just alterations to graphs. Today we're doing a particular kind of transformation called a translation, nothing to do with foreign language learning in French or things like that, but a translation is just a transformation, a change, that's moving a graph without changing its size or shape. So to do this for today and a lot of the rest of the chapter, you have to have some graphs to start with. So we need a little recap to earlier life from chapter 3, where we were graphing some graphs that made certain shapes all the time. Some of you might remember already what the x-squared graphs look like. Some of you might remember already what the absolute value graphs look like. If you do, great. If you don't, I'm going to do a quick summary here and then go on with that. You might also vaguely remember we graphed sometimes a thing like this. That is not appearing in this chapter. Okay? This was the graph that made steps. You remember graphing graphs that made steps? But that is no longer a part of our life. But in that same unit, we did some bars and some squares, and those are back. So if you completely blank on how to do a graph of something, you can always make a table. When it's y equals, you pick numbers for the opposite variable x. 0, 1, and 2 are always our favorites. So we could put 0 in for x where it gets squared and stays 0. 1 gets squared and stays 1. 2 gets squared and becomes 4. 2 times 2 is 4. And then we envision these as ordered pairs. 0, 0 is the origin. 1, 1 is located there. 2, 4 is right 2 and up 4. And we start to see sort of a shape, but not really a dominant shape. It's not a straight line, it's a little bit off. If we did more points, 3 would have given us 9, but I don't want to do 3 and 9 because I'd go off of my space. The best way to see what's going on with this is try some negatives, is what we historically did. If we tried -1 and squared, -1 times -1 is still +1. -1 would give us the same answer that 1 did. And we'd be able to go left 1, up 1, and get back to yesterday's idea of symmetry. Squaring was an even function. Squaring means it's symmetric to the y-axis. Squaring means whatever's on the right is going to get mirrored on the left. So -2 getting squared is also going to be +4. And this point is going to have a mirror match over there. Instead of right 2 up 4, it's left 2 up 4. We're going to make that basic shape following that basic pattern a lot. So I would highly suggest you get ready to always graph this bottom point, probably with the origin, called the vertex, is the bottom of the shape. Then be ready to go over 1 up 1, both sides. Be ready to go over 2 up 4 on both sides, and that's a quicker way to make that shape. That shape's going to get repeated over and over in the chapter, just getting moved. Translations of today means things are getting moved. So if I do this equation, somehow this would get moved. This adding 3 has changed the equation a little bit. Somehow that's going to make the graph get moved. On the notes paper for myself that I usually work from, it says something like, get some guesses and then make a table. So if you were here in person, I'd have people guess, hey, what do you think the 3 does? And people would guess all sorts of things, some of which would probably be bizarre because that's the way classes go with a group of 20 people. I'd have things like, it'll go up 3, it'll go left 3, it'll go right 3, it'll go down 3, and those all kind of maybe make sense. But I might have people saying like, it's gonna go right 7, and I would just like shake my head, at least internally, and wonder, what are they talking about? The 3 is gonna do something with the 3. So if we're not sure exactly what to do, which we're not, and you completely blank ever, you can make yourself a table, but I'm not gonna look to make a lot of tables here. Today we'll get some tables, but in your homework life, you want to try to do this table free. For now, just to try to learn what's happening. If we put in the 0, 0 squared is 0, adding 3 gets me 3. So that would give me a point that's headed up 3. If I put in 1, 1 squared is 1, adding 3 gets me 4, the point 1, 4 is there. And I put in 2. 2 squared is 4, adding 3 is 7. So I want to go over 2 and up 7. That's part of a U. We need the left side of a U, but this shouldn't take us as long as it did a second ago, because we might realize a little quicker this time. If we put in -1, what -1 times with -1 is 1, add 3, it's still the same 4, we're going to get this symmetry thing going again, where this point has a friend over here, that point's going to have a friend over there. It's the exact same shape as what we had. After doing that, there's absolutely no need for us to ever do a table on another x squared graph. What we need to do is recognize that this went up 3. So from the origin, go up 3 and do the vertex first. And then do the pattern I described to you a couple minutes ago. Go over 1 both ways to go up 1. Go over 2 both ways to go up 4. This is the exact same shape as this, and we're going to have that shape this chapter over and over and over and over again. Just memorize how to make that shape. If you were here in person, I would then ask for somebody to say, what is this graph, do you think, going to do? If this went up 3, what do you think this would be about? And I would think pretty quickly people would accurately start yelling, go down 2. There's always a strange voice or two out there in the wilderness that might yell some other sort of ridiculous thing, but most people would probably think, okay, adding 3, we go up 3. So I bet you subtracting 2 goes down 2. And that's exactly what it does. So if I wanted to graph this, tables are done. I'm not going to do another x squared table anytime soon. I would just go down 2 to do the vertex. I'd go over 1s to go up 1. Both on the left and the right to create symmetry. And I would go over 2 to go up 4, both on the left and on the right. You're going to want graph paper for this. If you own graph paper, great. If you don't own graph paper but own a printer, great. Somewhere on the all-knowing internet you should be able to find, Google printable graph paper, and you'll find it and print it and use it. If you don't own a printer and don't own graph paper, then I'm not sure what to tell you. I guess either try to, as neatly as you can, do the graphs like I'm doing them on the board with the little hash marks and stuff, or put off the graphing for a couple days if it's ever safe to go back into society and stores and buy graph paper. I guess you could do that, but I would not leave your house to buy graph paper. That's not really the spirit of what the government is asking us to do right now. I'd much rather you just do these weird little sketches like I have to on the board because I don't have graph paper for the board. And half the graphs in this chapter will be used. Half the graphs in this chapter are going to be absolute values which are different shape. So if you remember the shape, great. If you don't, graphing can always help you if you completely blank out. So the absolute, put in 0, absolute value of 0 is 0, absolute value of 1 is 1, absolute value of 2 is 2. We do these and get those 3 dots going, and it looks like a line, which it is not. The only way you get the full picture of this is try some negatives. The absolute value of -1 is also 1. The absolute value of -2 is also 2. So we get a similar symmetry thing to a minute ago, where we're going to get a point there and a point there, where these mirror each other, these two sides. And we are going to get all V shapes out of the absolute value graph. And I'd suggest you memorize this graph. If you memorize the other one already, you're already 3/5 done. Because out of the 5 dots I just did a second ago, 3 of them are in the same spots already. Start at the vertex again, like before. Over ones went up ones, like before. The only difference in the V's for the absolute values is that over 2 does not go up 4. It only goes up 2. Memorize that. It'll be a great help to us. What we then need to decide is, what is this 3 doing? And you might sense that this is doing a different thing than this, because there's bars that surround the 3. There's going to be half the problems in this chapter will have numbers that are inside parentheses or bars, and half the numbers will not. They'll be elsewhere. So I'll take a stroll over here to the right. These 2 problems have the number inside parentheses. That's a different family of idea than these numbers that are not inside the bars or the parentheses. So these are inside. They are like these 2, where those numbers are also inside. These 2, where the numbers aren't inside parentheses or bars, they're more in the family of what we just did, where the numbers were not in the parentheses or bars. So to try to figure out what this did for the first time, you might have to just try to like make a table. If you were here, I'd have you guess. People would yell all sorts of up 3 kind of stuff. 0 goes in, adds 3, that's 3. 1 adds 3 to get 4. 2 adds 3 to get 5. I could try to graph those to this point. 0, 3. 1, 4. 2, 5. So it's looking like it's gonna do something somewhere. To be sure what it's doing, we would need to try some negatives. If we put in a, wait, I just did the total wrong thing there. Rewind that. 0, 3, that was crazy. 0, 3 is there. 1, 4 is there. 2, 5 is there. My first mistake of the video, maybe. That was pretty goofy. But we need to put in some negatives. So if we put in -1, -1 adds 3, that gets us 2. So we would be there, and that's not helping us make a V. -2 adds 3 to get 1. So we would be -2, 1. That's still not a V. That's not helping us. -3 adds 3, gets 0. That's still not a V. That's still not helping us. And we never want to do this again. If I put in -4 and add 3, that's -1, but the bars make it 1. And finally, we're bouncing back up, and maybe we have a V. -5 adds 3 to get -2. The bars make it 2. And yes, we have a V. I never want to do a table that long again. What I want to do is take note that I just went left 3 squares. If we're adding 3 inside, we're going left 3. So subtracting 4 would therefore go right 4. So we want to go right 4. I need no table. I memorize that over 1s go up 1. I memorize that over 2s go up 2. And I make that V in about 20 seconds compared to that one took several minutes. And that's the way we want to go. Memorize the shape and memorize an idea of how the numbers go. So if I go through this cycle, you might want to pause and self-test, decide left, right, up, or down, and then re-pause me, or unpause me. This would go left 3. This would go right 2. Because these are like the ones over there. The numbers in the parentheses or bars go left, right, with the opposite sign of how it feels. Add 3, I realize, feels like it should go right, but it goes left. Sorry, that's how it works. The subtract 2 maybe feels like left 2, but it's not. It's right 2. The up-down works as it feels. Adding goes up, and subtracting goes down. And if you can memorize the ideas of how the numbers move you, all you can then do is just really quickly just graph the graphs. So let me do the left 3 graph real quick. If I want to graph this, I would just go left 3, make the vertex, over 1, up 1 on both sides, left and right, over 2, up 4 on both sides, left and right. And if I had graph paper, you'd clearly see every U I did this whole time is the exact same shape and size, it's only been moved. For this, we're going up 3, so I would just go up 3 for the vertex, but a different shape because the bars mean V's. So over 1, up 1, as everything is doing, but the over 2 is up 2's, left and right, to make ourselves a V. I got a couple minutes, so let me squeeze these in. The video at the 20-minute mark gets fussy, so I try to keep these 20 or less. If it's over 20, I have to cobble 2 of them together. Well, actually, I don't, but my director behind the scenes has to cobble them together. So quickly, if I go right 2 on this, I'd be there, and then just make normal shape. Over 1, up 1, both sides. Over 2, up 4, both sides. If I could draw, if the graph paper were here, those would be exact same shape, size, just move. This is down 4, 4. Over 1 is up 1 on both sides. Over 2 is up 2 on both sides. Make ourselves a V. Every V, same shape, same size, just different locations. Your homework tonight has no U's. There are no squares in tonight's homework. They are all V's. Every single shape is absolute values. I can read my book and then I'll return back to where I was. We would be working today from 391. The first 10 are all adding, subtracting, not in the bars. So everything on the first 10 are like this. Everything's going to move up or down. There's 2 at the end that are fractions. What you'd end up is middle of squares. If we were up a half, your original vertex would be half a square. When you go over 1, up 1, you're still like halfway through a square. You have to deal with that. 3/4 is in there, just kind of guesstimate. 3/4 is like most of a square. So when you go over 1, up 1, you're like most of the way up through a square. When you do 11 to 19, you're going right and left instead because the numbers are inside the bars. You could, for all 1 to 10, probably do it on one XY axis. You could end up with your homework just sort of looking like this with all of these all stacked up in a big stack. I don't really see a problem with that as long as you label number 1, number 2, number 3. The ones that go side by side, it's going to get crowded after about 4 of them. So I could probably squeeze on another couple of these. That might be reasonable-ish, but I wouldn't want 12 of those on the same graph paper. That's insane. So when you do the 11 to 19, maybe do like 3 per XY axis system. So best wishes. If you have questions, let me know and I'll try to answer them. Thank you.